Hey there, everybody. Let's get to recording some videos for Chapter 4. Chapter 4 is on applications of derivatives. The first section is on a very, very good topic. A lot of students find challenging, but it is an excellent topic. It's called related rates. Many real-world applications have quantities that are related to each other through formulas or equations that are changing with respect to time. The volume of a sphere or the area of a circle are related to its radius. So if the sphere or circle is changing size, the radius is changing size. The volume of a cone like this, or like this, or a cylinder like that, are related to both height and radius. In fact, let me write down the ones for the cone. The cone are 1/3 pi r squared h. That's for cone. And for cylinder, it is pi r squared h. So they're very similar to each other, just the cone has a 1/3 on it. Sphere is 4/3 pi r cubed. I need a pi in there. Pi r cubed. And the area of the circle is pi r squared. The sides of a triangle are related to its angles. There's lots of things we have with triangles. We have x squared plus, or a squared plus b squared equals c squared. I've got a triangle like this. I've got an angle theta there. We've got sine theta is opposite over hypotenuse. Cosine theta is adjacent over hypotenuse. Tangent theta is opposite over adjacent. So lots of formulas that have related stuff. Let's look at some examples. We're going to look at a spherical balloon. It's being filled with air at a constant rate of 5 centimeters cubed per second. How fast is the radius increasing when the radius is 2 centimeters? How about when it's 7 centimeters? I did write down the volume of the sphere up above. The surface area of a sphere, if it ever comes up in any of this, is 4 pi r squared. So we're going to look at this example and go through the steps to solving a related rates problem. First thing you want to do is assign variables to all changing quantities and draw a picture. So I got a picture of a sphere over here. I've got my radius r. V is the volume of it. It's kind of hard to depict a volume. The volume is changing because the balloon is getting blown up. So it's changing over time. So I made sure I said V was a function of time. And that means the radius is growing, which means r is a function of time. Next step, find an equation relating the variables in step 1. We had the volume equals 4/3 pi r cubed centimeters cubed. And then you want to write the known values from the problem in terms of our variables. So it did say, if we look at it up here, it said a spherical balloon, the constant rate of 5 centimeters, the balloon is being filled up. Being filled with air, a constant rate of 5 centimeters. So that's dV dt right here. And this says, how fast is the radius increasing with 2 centimeters? When it's 2 centimeters, 7 centimeters. So I listed them as two different radiuses. And we'll look at doing both in a second. Okay. Now that we've got things there and our information from the problem, those were the only numbers given, 5, 2, and 7. Next thing we want to do is differentiate both sides with respect to the independent variable, which is usually t. This is usually t for time, but not always. So we are going to, I wonder if I can erase just the highlight. Yeah, nice. All right, so we differentiate both sides with respect to the independent variable. Be sure to use the chain rule because we need a derivative. This is very much like implicit differentiation. So the implicit differentiation, use the chain rule. The new equations will show the relationships between the derivatives. So I started with this, and I took the time derivative. That's what we call it, time derivative. Take the time derivative. Maybe I'll put this down here. If you hear me say that, that means we're doing this right here, ddt on both sides. So we take the time derivative of volume, we get dv dt. We take the time derivative of the right side. The 4/3 pi is a constant. The derivative of r cubed is 3r squared times dr dt. And after cleaning it up, the 3's cancel, and I just get 4 pi r squared dr dt. Okay. At that point, we're going to substitute in any known values that we have and solve for the unknown quantity or rate of change. Sometimes we're looking for the rate of change. Sometimes we're looking for the quantity where that happens at. So dv dt we had was 5 centimeters cubed from up here. I'm going to start with R1, so we're doing 2 centimeters, and it's R squared, so we're squaring it. 2 centimeters squared is 4 centimeters squared. So 4 times 4 is 16. We've got 16 pi centimeters squared. And I put dr1 dt because I had two different radii that we're looking at. That's fun. Plural of radius is radii. So I divide by 16 pi centimeters squared. You'll notice that centimeters, there's 3 centimeters on top. It cancels those, leaving behind a 1. We just have centimeters squares left as units. And 5 over 16 pi, I did that in a calculator. I divided by 16 pi first, and then I did 16 pi in the calculator, and then did 5 divided by answer. I wrote out to 5 decimal places, 0.0995 centimeters per second. Then R2 just changed the radius to 7 centimeters. So 7 squared is 49, and 49 times 4 is 196. So we divide the 196 pi over, we get 5 centimeters cubed over 196 pi centimeters squared times seconds. Again, the centimeters cancel out. We're left with centimeters per second. And 5 over 196 pi, the radius is blowing up much more slowly. Look at that. It's another decimal place small. We got more zeros in front of it. It's much slower. The radius gets larger, slower. The larger we start at. Which makes sense. You've blown into a balloon, and it's easy to blow up the first part of the balloon, but next thing you know, you're puffing into it and it doesn't seem to be doing shit. All right, we got 2 more videos. We're going to do one with triangles and one with cones. And we'll be back for the next video in a second.